In this video, we're going to look at more of the trigonometric graphs. So recall graphing the sine and cosine functions that we looked at in the previous video, which were periodic functions. And for sine and cosine, we saw that both of them had period 2 pi. Since cosecant and secant are reciprocals of sine and cosine, they will also have the same initial period. Again, the period may change depending on the transformations, but to start out for just a secant curve or a cosecant curve, the period is going to be 2 pi. Unlike sine and cosine, cosecant and secant both have places where their values are undefined. So again, if you recall sine and cosine, the graphs there had domain all real numbers. For secant and cosecant, we have to find the places where it's undefined and remove those places from the graphs of the function. So every place sine or cosine is 0, the cosecant or secant, respectively, will be undefined. In general, our transformed functions have a similar form to our sine and cosine ones. So for cosecant, y will equal a cosecant of k times the quantity x minus b plus c. And for secant, y will equal secant of k times the quantity x minus b plus c. So again, these are the two general forms of the equations that we're going to be using to transform our functions. Now, just like with the sine and cosine graphs, a is our amplitude, b is going to be our phase shift, c is our vertical shift, and 2 pi over k is our period. Unlike our sine and cosine, again because the places these functions are undefined, we are going to have asymptotes. And so to find the asymptotes for cosecant, we're going to look at where kx minus bk, or the argument of our cosecant function, is equal to n pi, or places where the sine function is 0, so multiples of pi. For secant, we're going to look at the kx minus bk, so again that argument of the secant function, and we're going to determine where those are equal to pi over 2 plus n pi. So those are the places that cosine is 0. Okay. Now again, just like with our sine and cosine, we can graph these functions for basically any values on the domain, but usually we want to start out with just a single period. And we want kind of the practical period, which is going to be based on where those initial asymptotes and the initial period is. And so one complete period for both the cosecant and the secant curve is going to be from b to b plus 2 pi over k. So again, just like what we had for our sine and cosine. Now recall that cosecant of x is the same as 1 over sine of x, and secant of x is the same as 1 over cosine. So where sine and cosine have a range from -1 to 1, because we're reciprocating that, secant and cosecant have a range from -infinity to -1 and 1 to infinity. This makes visualizing these graphs somewhat difficult. And what I mean by this is the fact that there are places it's undefined, the places where these asymptotes are going to be, and now knowing that the range has this huge gap in it, it makes it difficult to visualize these. So what we do is we use the graphs of cosine and sine to actually graph the secant and cosecant. So let's look at a couple of examples. In this first example, we want to graph y equals 5 secant of 3x minus pi over 2 for 2 periods. So again, the first thing we're going to want to do is we're going to start by finding the information just like we did for sines and cosines, and then we're going to use that information to figure out what the in this case, cosine graph looks like, and use that to get our graph of the secant. So for this graph, again, we first want to begin by rewriting our function. Notice the original graph we were given, or function we were given, is not in the general form. So we want to pull that 3 out so that we can get it into its standard form. So we can see that A is going to be 5. The absolute value of A is 5. That's our amplitude. Our phase shift is going to be pi over 6. Our vertical shift, there is none. And our period is going to be 2 pi over 3. Now again, because this function has places where it's undefined, we need to find the asymptotes. And so again, we'll set the argument equal to pi over 2 plus n pi and solve for x, which we see is going to be pi over 3 plus n pi. Now we can determine the two periods that we're going to want to graph. So in this case, our phase shift is pi over 6, so we're going to start our interval at pi over 6, and we can use the asymptotes and the period to determine two full periods of the graph. So in this case, our period is 2 pi over 3. If we like, we can think of that as 4 pi over 6. So we're going to add 4 pi over 6 times 2, or 8 pi over 6, to get 9 pi over 6, or 3 pi over 2. So there's the interval for the two periods that we're going to graph. Okay. So now we're going to graph our cosine function, which is basically going to look like 5 cosine of 3x minus pi over 2. So here we can see the graph of the cosine function, which is not what we want to graph. Again, we want to graph the secant. But again, we're going to use this to get our asymptotes and our highs and lows. And we can see again with the amplitude, it's going from -5 to 5. It's shifted over pi over 6 units. There's no vertical shift, and it has a period of pi over 3, 2 pi over 3. So now to get our secant curve, we're going to start by sketching in the asymptotes, and then using the highs and lows to find the lows and highs of the secant curve. So remember, it's a reciprocal of the graph, so everywhere that cosine has a high value, secant is going to have a low value. And everywhere cosine has a low value, secant is going to have a high value. So again, looking at our curve, here the red graph is our graph of the secant curve that we want. And again, you'll notice the asymptotes are every place the cosine graph crosses the x-axis. The low points are the high points of the cosine graph, and the high points are the low points of the cosine graph. And so we can see that this does meet the conditions that the range is from -infinity to -5 and from 5 to infinity. So there's that gap. And we have all of the asymptotes put in place, which we can verify with our equation x equals pi over 3 plus n pi. Okay, so let's look at the second one here. So let's look at the cosecant. So y equals 2 cosecant of pi x minus pi over 3 plus 1, and we want to graph this for two periods. So similarly to what we did for the secant curve, we're going to start by rewriting the equation in its general form and finding our values for the variables. So here we can see that y equals 2 cosecant of pi times the quantity x minus a third plus 1. So our amplitude is 2, our phase shift is a third, c is 1, so we're going to shift it up 1 unit. The period for this graph is 2. Now, notice that there's no pi in this, so it's not going to be like the other graphs. We can actually graph this using integer values. And the asymptotes, again, we found the equations for those. They're going to be at 1/3 plus n for any integer n. So again, in this graph, we want to graph two periods of this. So again, we'll use our b, meaning a third, and two periods, which in this case would be a total of 4 units, to get our 2-period interval. So our 2 periods for this graph is going to be the interval from 1/3 to 13/3. So now that we have the 2-period interval from 1/3 to 13/3, we can graph this function. Now I'm going to show a different way of graphing this than we did the last one. So the last one we used the cosine function to graph the secant. But again, just like our sines and cosines, I should be able to just graph it based on the equation. And so here we're going to use the phase shift and the interval as well as the asymptotes to figure out what the graph is going to look like. So to start the graph, we're going to find our highs and lows. So again, we can think the cosecant is normally from negative infinity to negative 1, and then from 1 to infinity. Because we have an amplitude of 2, it's going to go from negative infinity to negative 2, and from 2 to infinity, and then we're shifting that up 1 unit. So this means all of our low points are going to be from 3 and up, and all of our high points are going to be from negative infinity to negative 1. So if I pick 5 over 6, which is halfway between those two values, and I put it into my function, so pi times 5, 6 will give me 5 pi over 6 minus pi over 3 will give me pi over 2. Cosecant of that turns out to be 1, and then if I do my amplitude and my phase shift, I see I get a positive 3. So in there, I'm going to get my high point, my low point. It's going to be above the x-axis, but it's a low point. So there would be our graph for y equals 2 cosecant pi x minus pi over 3 plus 1. Now in both cases for these graphs, again, you can graph them by point plotting, or you can use the two different techniques shown here. Okay. Just like your sines and cosines, what we're looking for is that you have the right points, meaning those nice end values, the midpoints, the asymptotes, and you have the correct directions on them. So whether it's above the axis or below, if it's something that's going up to infinity or something going down to negative infinity, having the right hills and valleys, so to speak. So now that we've looked at sine, cosine, secant, and cosecant, let's look at the tangent and cotangent functions. To start off, we're going to look at the tangent function. These two functions are a little different because they both have period pi. So this means that tangent of x plus pi is going to equal tangent of x. So unlike the 2 pi period that the other four functions have. Also, we notice that tangent of x from our reciprocal properties is sine x over cosine x. So this means tangent is going to be undefined at all the places where the cosine is 0. Okay? In other words, we're going to have asymptotes for this function. And they're going to be the same asymptotes that we saw for the secant graph. In general, our transformed function for tangent looks like y equals a times the tangent of k x minus b plus c. So very similar to what we've seen before. A is still the amplitude. Here this means something a little different. So because tangent has a range of all real numbers, what we're going to see is that the amplitude is basically just going to tell on the symmetric pieces how far away from the center value it is. And that may not make much sense now, but you'll see it when we look at the graphs. B is going to be the phase shift, so again, just the horizontal shifting. C is our vertical shift. Pi over k is the period. So again, be aware that it's no longer a 2 pi because we're now looking at a tangent function. The asymptotes, again, are where our cosine function is 0. So we're going to take the argument kx minus bk and let it equal the places cosine equals 0. So pi over 2 plus n pi. Here, because this function has set asymptotes, one complete period is determined by the asymptotes of the graph. Okay, so in this case, one complete period would be from negative pi over 2k plus b to pi over 2k plus b. And again, depending on how many intervals you want, or if you're given set values, that'll determine what you're going to use to graph. So let's look at a couple of graphs of tangent. So for this first one, y equals tangent of 2/3 x minus pi over 6. We want to graph this over one period. So here, again, we need to start by rewriting the function into the correct general form, and finding our values for the different variables. So rewriting our function, y is going to equal tangent of 2/3 times the quantity x minus pi over 4. This means that our amplitude is 1, so it's no change from the regular tangent graph. B is going to equal pi over 4, so that's our phase shift. There is no vertical shift, and our period is going to be 3 pi over 2. The asymptotes, solving our equation, we see that x equals pi plus 3 pi over 2n. So starting at pi, every 3/2 pi, we're going to have another asymptote. Now again, to get the interval, our interval starts from the negative side of 0. So normally it would start at negative pi over 2. In this case, looking at our b was at pi over 4, so if I take negative 1 as my n, that gives me my first asymptote, and then putting in 0 will give me the second asymptote. So one period of this function is going to be from negative pi over 2 to pi. So setting up our graph, we're going to have our amplitude at 1, so again, no change. Again, that's just telling us the symmetry. We're going to go from negative pi over 2 to pi, and we're going to have asymptotes at every 3 pi over 2n. Notice the middle points of those asymptotes. So looking from negative pi over 2 to pi, the middle point of that is at pi over 2. And if I look at, pi over 4, if I look at that middle point, that value is actually going to be 0. That's going to zero out that argument, and it's going to be where sine is 0. So the whole function is 0. Okay, so let's look at the graph of this function. So here we can see that the graph of our tangent, those values of 1 just tell us kind of where it starts curving towards the asymptotes. Same thing on the negative side when it goes to negative 1, where it starts curving towards that left asymptote. And so from our interval from negative pi over 2 to pi, there's one period of our tangent curve. Let's look at one more. So here we want to graph y equals 1/2 tangent of pi x minus pi over the interval from negative 2 to 4. So here again, we're going to start by rewriting the function and finding our values for our variables. The other thing to notice is when we look at our interval that we're asked to graph, notice there's no pi's in there, which tells us when we start rewriting our function, our phase shift and our asymptotes should be in terms of integer values. So if I'm getting values of pi or pi over 3 or things like that, I know I'm doing something wrong. So for this one, y equals 1/2 tangent of pi times the quantity x minus pi. Our amplitude is going to be 1/2, our phase shift is 1, our period is 1, and our asymptotes, when we solve our equation, are 3/2 plus n. So again, that's just every integer value more than 3/2. So in this case, we want to graph it over the interval from negative 2 to 4. So I don't need to look at the periods here, I just need to figure out where the asymptotes are on that particular interval. So on the interval from negative 2 to 4, we can see that we're going to have 6 asymptotes. We'll start them when n equals 0, so that'll be at 3/2. Add 1, 2, 3 to get the positive ones, and subtract 1, 2, and 3 to get the negative ones. From there, we can go ahead and graph our tangent function. So again, for tangent, in between the asymptotes, we know it's going to be an increasing function, and halfway between those asymptotes, we're going to have the place where it's zeroed. Where it starts increasing towards the asymptote and decreasing towards the asymptote is where that amplitude value is. So here, on this case, we're looking at positive and negative 1/2. Again, halfway between the center and the asymptotes. So here's a sketch of our graph. And again, we want to graph it from negative 2 to 4. So notice at negative 2 and at 4, I don't finish the tangent curves for those asymptotes, I'm only going to those particular values. Okay, and again we can kind of see as I move through the half and the negative 1/2, that's where the tangent curve is going to bend towards the asymptotes. So at this point we've looked at all of the curves except for our cotangent. So now let's consider our cotangent. Like our tangent function, this has period pi, so cotangent of x plus pi is going to equal cotangent of x. Also, like our tangent, cotangent is a reciprocal function. In this case, cosine of x over sine of x. So cotangent is going to be undefined in all of the same places where sine of x is equal to 0. In general, our transformed function for cotangent looks like y equals a cotangent of k times the quantity x minus b plus c. Again, very similar to all of our other trig functions. A again is the amplitude, which again determines the variation in the symmetry, much like our tangent function. B is our phase shift, C is our vertical shift, pi over k is our period. Again, notice it's a pi, not a 2 pi. The asymptotes for this one, again, are places where sine is 0, so kx minus bk, the argument for our cotangent, is going to equal n pi. One complete period of our cotangent curve is going to be between b and b plus pi over k. Okay. Again, if you are asked for other periods, meaning multiple periods of the graph, or if you're asked for specific intervals, you're going to want to adjust this complete period. Okay. So let's look at graphing a couple of the cotangent functions. So this first one, y equals cotangent 2x minus pi over 2, we want to graph this over one period. So again, just like our other functions, we're going to start by rewriting our function and finding our values for our variables. So in this case, y equals cotangent of 2 times the quantity x minus pi over 4. Our amplitude is 1, our phase shift is pi over 4, there is no vertical shift, and our period is pi over 2. The asymptotes in this case are going to be pi over 4 plus n pi over 2. And since we want to graph one period of this, that means we're going to start at pi over 4 and go a period of pi over 2. So one period is going to be pi over 4 to 3 pi over 4. Notice, like our cotangent, we are not including these endpoints because those are going to be asymptotes of our function. So now we just want to go ahead and use this information to get the graph. One thing to remember about your cotangent is because your cosine is on top, this is going to be a decreasing function. So as my values get more positive for x, the value for the cotangent is going to get more and more negative. So here is one period of the graph of y equal cotangent 2x minus pi over 2. Again, notice as my x values move to the right, my function value is decreasing. My values from the center point are 1 unit away, and my asymptotes are at the end values of my interval. Let's look at one more graph. Let's graph y equal 3 cotangent pi over 2 times the quantity x plus 3 minus 1. And for this one, we want to graph it over the interval from negative 3 to 3. Now again, we're going to start out the same way, rewrite our function. In this case, it's already rewritten. So we're going to find our variables. And then again, notice our interval is in terms of integers. So when we go to solve for the asymptotes and our phase shift and all of those quantities, they should also be in terms of integers. So for this function, our amplitude is going to be 3. Our phase shift is negative 3, so we're actually moving to the left 3 units. Our c is going to be negative 1, so we're going to shift the graph down 1 unit. And our period is going to be 2. In this case, our asymptote, solving for when the sine values are 0, we get x equals 2n minus 3. So again, these are going to be integer values. So now we can go ahead and plot this. In this case, because we're given a specific interval, we don't have to look for the period. We just need to find where the asymptotes are on that particular interval. So in this case, our interval again from negative 3 to 3, we can see the 2n minus 3 is going to give us 4 asymptotes on that interval. So 1 at each of the endpoints, and then 1 at -1 and +1. From there, we need to find our midpoints of those asymptotes, which happen to be at -2, 0, and 2. And those are going to have center points down 1 unit, okay, because we're shifting the entire graph down by 1. So instead of having those on the x-axis, they're going to be at -1. And then from there, our halfway points between the centers and the asymptotes, those amplitudes are going to be at 3. So from the -1, we're going to measure 3 units up and 3 units down, and that's where it's going to make its curves. So here's our graph of the cotangent function, 3 cotangent pi over 2x plus 3 minus 1. And again, we can see how it's stretched a little bit, that amplitude of 3, and the period has shrunk a little bit over that -3 to 3 interval.